All right, so to start us out here, when we think back to learning how to graph the very first time, before you knew that mx plus b existed and you could just draw a graph by finding b in the slope, how did we figure out what a graph looks like? Before we knew about y equals mx plus b, like if I gave a bunch of 7th graders this, Naomi, I want you to say that much louder. You're going to find some points. Now, when you organize those points, they're typically in a table. Tabular form is a fancy word for that, like a tabular interpretation just means we're thinking about a function on a table. By a table, all I mean, and this is just pink for think real quick, if I give a 7th grade who's in Ms. Jarvis' class this problem, they're not just going to graph it right away, I don't think. I think that they're going to take some time and they're going to say, hey, for an x, I'm going to find the associated what? The y value. Now, we're not going to build this whole table together, but I do just want to check some things. In this problem, what x's might you pick? 0. And we could get the value, it's 4. And I'm not worried about the middle part right now. Is that enough? 1 point will give me a line. So we know that it's 2 points for a line, but I would imagine that in 7th grade when you did it, it was probably like 5 points for a line. Lando, you better be able to do this without the calculator also, just so you know. Okay, give me another point then. 1 and it's 6. And then we might get a 2 and it's an 8. And if we put all these points on the coordinate plane, we'll have a straight line and we'll have our graph. Everybody agree with that? Okay, now, does it really matter what values of x we pick on this one? Not really. Now, if I want, we're going to do a couple little things. It's kind of like a warm-up, but it's not going to be super formal. It's going to be you guys talking with one another on this. Okay, what if you don't have to make the whole table for me, but I want you to think about what x values would you pick if instead of y equals 2x plus 4 or a linear function, what if I gave you something like this? We'll make it 12 over 2x. And I lied. I'm going to make that 12 over x plus 1. I want with your neighbors, and if you need to build the table, you can. Like, you're going to have a hard time thinking all out. I don't really care about the f of x part, but I want you to pick 4 values for x that you would use and convince your neighbor, yourself, and the whole class here in a couple minutes that your numbers are good numbers for this. So there's infinitely many choices you could pick. There's one that you can't. There's a -1 you can't. But I want to see 4 values that you would pick. Talk it out. I'm going to give you guys like 90 seconds. Go. For this, if you are struggling and neither I nor Miss Sweet was able to get around and talk to you, I'm going to suggest one, and I want you guys to, it will work, but I want you to tell me why it's not nice. Now, I saw a lot of 0, 1, 2, 3s, which reminds me of when we started doing quadratics. If they were all centered on the y-axis, those are the natural points you would pick. Remember when we actually do quadratics, and if we know where the vertex is or we find the vertex, we pick points centered around the vertex, not just the y-axis. But here's my claim. I think that this is a bad number to choose. Now, it will work, King, I think. King, I am so thirsty. Will you go grab me a drink? Cool. All right. Why is this not a super nice number? Yeah, when we do this, we could knock it out, but it's 12 over... Why are we laughing? He assumed that I saw him sleeping and I wanted him to go get a drink from the water. Yeah, he did what he was supposed to. You all are in the wrong. All right. This number's not terrible, but it's not super nice. What's 12/7 real quick without a calculator? Me neither. I mean, I could estimate it, but I don't know what a 7th is. That's a really weird. King, I just want you to walk to get a drink because you were falling asleep. I just want you to stretch your legs. You were all wrong, apparently. All right. So this is okay, but it's not the nicest number. Give me a nice number. 0 works really well. Why? 12 over 1 is an easy fraction. Now, 0, 1, and 2 coincidentally all work. 3, does 3 work? Why? It makes it 12 divided by 4. Whatever we're picking, do you guys agree? If we think about it a little bit, it's so much easier to graph those points, 12 or 3, or if we pick a 2, it's a 4. Like, those are easy points to plot. This point is doable, but it's not as easy. Can we all agree with that? Now, if we can recognize that idea, then this next example, we're going to name our section real quick, and I'm going to ask you guys, you're going to make a parent function for me. which, gosh, it's super embarrassing, but what's a parent function? 30 seconds with 15 seconds with your neighbor is going to call somebody random. What's a parent function? So just purely semantically, is a pregnant person a parent yet? I don't know. I don't know the answer. Just that's my first thought when I heard it. Like, I don't know. I don't get to claim the unborn child on my taxes yet. So Okay, but I forgot the question because that was an interesting thing I heard. Okay, what is it? What's a parent function? So that's an example of a parent function. Y equals x is a parent function for which class of functions? Linears. Good job, Angel. What's the parent for the quadratics? X squared. What's the parent function for the cubics? Do we do logarithms in this class yet? Bummer. Okay. What's the parent function for the reciprocal functions? Louder. 1 over x. It's all the rational stuff that we were talking about last chapter. Okay, so what are we talking about this chapter? We're not talking about rational functions. What has been like our entire focus throughout the first couple sections? Oh my, radicals. Cool. Shaka brah, there we go. Today, our functions are not lame, but rather they're what? Rad. Radical functions. Okay, we get to graph these bad boys today. So to start us off, here's my challenge for you. The thing that we did just now where we said, let's pick the nice x's, it was not in vain. There was a total reason behind it, and I hope I have convinced you all that there are some nicer values that we can pick with the understanding that most numbers work, but there are some that are nicer than others. For that, we are going to be talking first today about radical functions is obviously where we're getting to, but let's start with the easiest radical. What's the easiest index to deal with? The 0th root of something? So when I say root 5, what am I, like that's the simplest root that we have. And it's what root? Square. So the lowest index on any radical that we get is a 2 or a square. I would take either. Okay, so let's start there. We're going to build up this intuition at least with our square root functions. I would put func in my notes if I were you, just to save a little time, but our focus is on square root functions. Now, if we need a definition, we can sneak it in, but these are going to be functions that have a variable where, do you think? In the square root. I'm just going to say vars, because that's what the shorthand on your yellow calculators are. The variables are in the radicand, which is a really convenient way to define this because it doesn't matter whether we're talking a square root function or a cube root or a fifth root function. Irrelevant. The variables are in the radicand, or at least there are variables in the radicand, not necessarily exclusively. Okay, with that said, if we're looking at square roots, which is our first focus, what do you think is the parent function? And I don't know why that's coming out caps because we've defined that. I'm also writing very bold. So let's fix all that stuff. What is the parent function from which every other square root function will simply be a transformation of? Y equals the square root of x. Can anybody come up with a simpler square root function than that? So you've given me a different form of it, which is awesome. But whether I write root x or x to the 1/2, is it really any different? So that'd be x squared, though, wouldn't it? You're not giving me a square root in that situation. So I like either of those. I'm going to call it f of x rather, but we're going to say f of x is, and I'm going to write it as root x. Now, quick check. We're going to just agree no calculators on this one. Cool. For this, how many of you guys know what this graph looks like off the top of your head? Wonderful. Okay, check it out. I'm okay with that. Your job for the next 3 minutes, if it takes that long, is you're going to make a table. And I always do these lovely 3-column tables. I'm not going to require that you do unless you keep getting the f of x points wrong, in which case I'll make you show me how you're getting it all. I do suggest it for everybody, just for the record. But while we go through this, your job for the next couple of minutes, and I'll pause this, is I want you to construct the graph of this. And my only requirement for this one, and we won't use this many in the future, but in this column right here, I want you and your table mates, you're going to find me 5 values that are going to work nicely for this. Now, we might not all have the same values. That's okay. But you're not allowed to touch a calculator. That's the biggest rule right now. No calculators. Cool. 3 minutes. Make me a table. Sketch a graph of it if you are able. I want you to try to sketch the graph of it. Let's see what we come up with. Talk it out. This was the most common table that I saw, and a lot of you guys started here. Now, here's my only question for you. Do I like to try to be efficient sometimes? Should we all strive to be efficient with stuff? For sure. If we try to plot these points, we're just going to see there's one person in this classroom that I saw, and there might be more, but there's only one person whose page that I saw that really exemplifies what I would call efficient with this problem, which that's not saying that everybody else did it wrong. There's one person here who did it exactly how I would love to see it done. Okay, looking at this, if we have this table, first thing that I notice is if we're graphing it, a lot of you guys, and it's okay, but a lot of you guys are stuck on this idea of making big scale like this. What's the smallest x value that shows up on my table and most of yours? So that's a y value. What about x value? 4. Am I ever going to use anything over here then? Now, it's purely in the in an aesthetic or how does it look and how does it feel. If we don't use any of the negative stuff on our table, and I'll leave room for it just in case it shows up, but we're pretty much focused on the positive stuff. So let's see. I'm going to go all the way out to 40. And I'm going to really roughly plot these because these numbers get so big. So there's 20 and 10 and 30. Okay, I'm going to go up to 6, and then there's 3, and we're just making a really quick sketch. Okay, from this table, if we start plotting these points, I can plot 4, 2, and that's like right here, 4, 2-ish. And I'm not putting a whole lot of energy into this. I will highlight it. I'm going to make it a little bit further over. There we go. 4, 2. Okay, I'm only going to do a few of these slowly, but we'll start working it. Here's 9, 3. Here is 16, and it looks like there's 10 and 15, 16, and 4. And then 25 is here and 5. And 36 and 6 is way over here. Okay. Not a whole lot of energy into this, but if you plot these 5 points, we should all get the same sort of shape. First off, do we have a line? Do we? Show me a line with your hands. Or with your arm, rather. Okay, now make it bendy like that. Don't break your arm. So, me too, just for the record. But you can't bend your arm, right? There's bones in here. Okay, so I don't think it's a line. If it's not a line, what do we call it? Okay, so it's a curve. I'm all right with that. Okay, so we have a curve up on the board. Now, with what we've selected, I think that we run a pretty big risk. I can see that it looks like it's going this way. I'm pretty sure. Do you guys agree with that? Like, it looks like it's kind of mellowing out. Does it keep going any further left? Like, does it go... Can I pick any other x value smaller than 4? So, we'll get there. 1 is the next one that's nice, I think. Okay, a lot of you guys had 1 on your table. How many of you in here started with 1? Okay, we're getting closer to where I want you to start. Do we like stuff the easy way or the hard way? So here's 1, 1. I agree. I hope we all like... Actually, I'll make it even more 1, 1-y. It's like over here. It's like here, actually. Goodness, I can't find it. It's whatever. Okay, is there another number we could use? Mark is the one person who, in efficiency sense, did exactly what I would do. Do you want to take easier square roots or harder? Yeah, we should all agree with that. What's the easiest square root you know? Smaller than 1. What's the square root of 0? 0. You definitely can take the square root of 0. 0 times 0 is, by definition, the square root of 0 must be 0. Okay, can I pick smaller values and still graph them? Let's try. If I use -1, what's the square root of -1? I. So here's my big question. Here's roughly -1. Show me where to go to get to I. like toward me, realistically, if we wanted x and y and I, we would need a third dimension to this thing. Can we do anything less than 0? No. So when we're looking at this, if you started with 4, it's not bad. But if you didn't do these extra points, I think the natural mistake to make would be to do something like this, because you aren't forced to think about what numbers can you take the square root of. What did we just decide was the smallest number we could plug in? A 0, which means this actual graph, and I'm going to miss some of these points, but we'll try to make them line up. This is what our square root parent function really truly looks like. Now, on the calculator, we'll see the exact same graph. There's always 2 follow-up questions that we have with these. Every time that we start looking at a new type of graph, and you get a lot of these questions as we keep doing the graphs. But if I want to talk about what can I plug into a function, gosh, there's a word for that, I think. What values of x can I actually plug in and get values to spit out at? All the x's that I can plug in. And all the y's that it spits out, those have very specific names. Domain and range. What is the domain of our lovely parent function? Ooh, so I heard 2 different things. I heard all reals, which I do not agree with. I heard all positives, which I do not agree with. Ooh, what's the difference between all positives? And then Michael whispered loudly, so I guess he spoke. I don't know, that's weird phrasing on my part. What's the difference between all positives and then he said 0? Is 0 is not positive? Is 0 negative? No, so rather than saying all positives, the more wordy way to say this would be all non-negative numbers. That's how we include 0 in it. If I want to write it here, we're going to write it set builder first. It's the x such that, what do we require that x is greater than or equal to? 0. Okay, if we're looking at this, any real number greater than 0 would work. Do you guys agree with that? Okay, I'm fine with this. In an interval, what would it be? X is in the interval. I start at 0 and I go how far? Infinitely far. Now, here's the big question. I know I can't touch infinity, so it gets a parenthesis. Am I allowed to touch 0? So what symbol do I use here? We bracket. Awesome. Okay. If we pick nice numbers, this should theoretically be pretty easy to deal with. Do you guys agree? Now, as we're looking at these, your book, sorry, we need the range too. My bad. The range of f of x. It's the set of all what? The y values, such that, what do you notice about any of the y values that we get out? Is there a smallest? Is there a biggest? The smallest is 0. Now, this graph, because we only have a small section of it, it kind of looks like we have an asymptote to me. A little bit it looks like that. But if we take a step back and just think about it, we should be able to discern whether it does or doesn't. If you pick a really big number and ask the square root of it, is it bigger than the numbers we have here? If you pick an even bigger number, is it bigger than the numbers that were there already? Like, square roots never stop getting bigger, right? The square root of 100 is 10. The square root of 10,000 is 100, and they just keep getting bigger and bigger. It starts to slow down for sure, but does it ever stop getting bigger? So what's the range? Ooh, it's not infinity to infinity. 0 to infinity, which that's the interval form. That would be saying y is greater than or equal to? Indeed. Okay, as we are looking at this, today we're just going to be able to lay the foundation for tomorrow's stuff, and I don't want you to like cry and freak out, mass hysteria or anything, but I don't think I'm going to be able to give you homework today. Tomorrow in class, what we're going to do and where we're going to jump in, so just a heads up, I'm not done yet, just so you guys know. Graphing, we're going to jump up a pretty big looking step, but we do this every time. Tomorrow, to start class, we're going to be graphing not just the parent function, but we're going to be graphing things of the form a times the nth root of bx minus c plus k. Cool. I'm going to leave you on that cliffhanger so we can see how all that works tomorrow. You guys have a wonderful day, or don't. I'm not your boss.